our other sponsors, ANSYS, Pagliacci, Victrola, they were here with us last year, and we are so proud to have them along for the ride this time around. Space Frontier Foundation is supporting us with another New Space ticket, and we'll talk about that later. Seattle Makers has done some amazing things for us, and Adas was our host for the Mixer on Tuesday, which feels like a really long time ago. Okay, let me talk about our judging panel. It's a great group. We have Robert Kahn, Director of Software Engineering and Space Operations at Spaceflight Industry, and also space imaging company Black Sky. We have Todd Hossain, who is a partner at Second News and co-founder of the Space Apps Challenge. A pretty amazing VIP to be joining us. First time at Space Apps Seattle. This is the shortest distance he's ever had to travel to get to a Space Apps event. And we're so lucky to have him. Ray Mamadura, Principal Technologist for Avionics at Blue Origin. Good to see you again, Ray. Ray was a judge last year. So happy to have him back. Bob Zimmering, who was up here giving a talk before, is the Director of Quality Assurance and for strategic and missile defense systems at Lockheed Martin, and Steve Dorolic, who is also at Lockheed Martin, a fellow and chief architect for Lockheed Martin Space IT. So let's talk a little bit about the local awards categories. We're going to be awarding in Best Use of Hardware, Best Use of Data, Best Mission Concept, and Most Inspirational Hack. And Lockheed Martin is also providing a Rising Star Award to the Best Student-Led Project. We're also going to be nominating 2 projects to go to global judging level. Those projects, if you go all the way through multiple rounds, which will take a few months, and are judged in a virtual competition. It's a tour of Kennedy Space Center, which is pretty cool, and just for Space Apps Challenge winners, flight and lodging not included. Prizes are actually really cool. Each winning team will get a Voyager Golden Record set. You know the Voyager probe? Everybody knows Voyager, yes? You know about the Golden Record, right? It's designed to be read by extraterrestrial intelligence and has information and sounds from the Earth. And the Rising Star Award will be a 3D printed Orion capsule model. Looks really cool. They're not here on site. We're not going to be handing them out, but that's what will be delivered to the teams. All winners, each individual on the team will get an additional $300 in AWS credits. And our global nominees will get a $50 Pagliacci gift card, and the other will get a Victrola gift basket. And it is about continuing the hackathon, right? Continuing your project and keeping your team together, because it's the relationships that you've made here that are so important. We will also have a competition for the One New Space 2020 conference ticket. And I'll talk about how that goes. Okay, so before we get into presentations though, I'd like Todd Hossain to come up and give his talk to you and his unique perspective on connections and space apps.
Thanks, Mike. What's that? Hi, how are you? Did anybody get sleep last night? Not so much? So how many here built something amazing over the last 2 days with no help from any other human? That's because that's a myth. Nothing that we do obviously happens without the help of a ton of other humans. And as kind of like the world has developed this growing body of research around like what makes an amazing team, it turns out that the more different that the humans that we're working with are to us in terms of how they view the world and how they grew up and who they are, the more likely we are to be smart and like come up with really creative solutions and things like that. Can you hear me?
Yes.
So I'm between you all on a ton of presentations, so I'm going to give you a very, very rapid walkthrough of a little bit about what it took to kind of get to a pretty amazing day and a pretty amazing weekend, and give you a little context about what's happening in the rest of the world sort of right now. So about 10 years ago, a lot of these data sets that you're working with were there, but they weren't accessible. They weren't really confidential, but they weren't really accessible. It was really hard to find these giant data sets that anybody had, let alone non-confidential data like that NASA had. And so a lot of us worked really hard to figure out how can we release the data, because there's all these brilliant, amazing humans, a small subset of which are sitting here in this room today, which do really, really smart work, are really smart coders, are really smart creatives, are really smart designers, but might not necessarily have expertise around space-generated data or space science, per se. And so we worked really hard to get a bunch of data out there, and we realized, oh my God, the data has no context. People aren't going to do anything else. So we put this huge efforts to create a bunch of metadata. But then it turned out that it wasn't just technological context that we actually needed, or technical context, we also needed human context. And so we worked really hard to start building communities of people, both on the challenge side of things, which is like, okay, well, let's understand what some of the biggest challenges are that an organization like NASA is facing, or other organizations are facing. But then also start to build communities on the side of the people that are actually doing really interesting things with data to actually start to develop solutions. Because again, if the more we have diversity, the smarter the solutions that we're actually going to get. The people that are smartest about the problem aren't always the people that are going to give you the most innovative solutions. The key is always to bring other people into the room that might come at something with a different angle, whether it's somebody much younger, much older, from a totally different culture, from a totally different sort of context. Most of your heads are very much in like code and in solutions and in the stuff that you've been doing while you haven't been sleeping for the last couple days. As you get up and give the presentations, remember that you're doing so alongside over 25,000 other people this weekend. Coming from over 240 cities around the world, from over 80 countries. So these are people that are 7-year-old and that are 90. These are people from radically different cultural, socioeconomic, political contexts that are coming around similar sets of data that have been generated through space, and trying to build solutions to real problems that we're facing here and in space. And I think in an era where the problems that are kind of facing humanity don't always reflect the clean lines that we've drawn around ourselves. These are problems that kind of go over there. And so as we're trying to think about solutions to big problems, we're going to need these types of Herculean efforts. And so we've worked a lot of time working as a family unit. We've spent a lot of time as human civilization working as tribes. We've started to figure out how to work as cities. We've started to figure out how to work as nations. But we're really kind of early in figuring out how do we work as a global community. And when you're sitting over here with people from over 80 other countries around the world, like literally at the same time, literally looking at the same data, literally looking at the same problems, but coming up with unique solutions, makes me feel like we're getting one step closer to do that. So thank you so much on behalf of NASA, on behalf of the global organizing team, and certainly on behalf of Second News. Thank you so much for the organizers, the sponsors, but most important, you all that have been hustling for 2 days to make something amazing happen. So thank you so much for having me.
Okay, thank you, Todd. We got all our judges in place. I think it's time to start the presentations. So this is how we're going to do it. We're going to announce who is up, and we're going to announce who's on deck. When you are on deck, go on over there, right? And you come along up this side. right? People who are along the window, except for Reese, who's running the live stream, might be a little bumpy there. But what I'd like you all to do is move as quickly and efficiently as possible to here, right? Plug in, tech check, and you've done your tech check, so you should be all good. And be sure to clear away from the live stream camera, which is fine. Begin your presentation. When you're done, exit that way. You are going to get a warning when you've got 1 minute left. And then you're going to get a warning when you've got 30 seconds left, right? And then we will applaud when your time is up. We've got so many teams, we need to keep this moving quickly. Has everybody got that? Makes sense? Is everybody excited?
Yeah.
So before we get into it, firstly, we want to congratulate all of you for all the hard work that's taken to get to this point. To all of our participants, to everyone who's presenting. I had the pleasure of getting to meet a lot of you, and I know some of you right now are a little bit nervous. That's a good thing. Being nervous in a context like this, it means you're trying something new. It means you're collaborating with new people and you're trying new ideas, and that's what's going to get us to a point where we can develop new ideas that will really change the world. And so if you feel excited, I also encourage you to feel more excited. If you feel nervous, have fun. So let's all have fun in that spirit. Thank you.
Our very first team up, data sniffers.
Yes, why data sniffers data?
Hi, we're Team Data Sniffers, as you might have heard, and we're a group of grad students from UW majoring in data science and business intelligence. The topic that we've taken up for today is to bloom or not to bloom. And here we sort of attempt to figure out how to predict algal blooms and how to sort of use that data to prevent harm to both animal and human life. We are Ayush, Heath, Anirudh, and Vaibhav. And for the next 4 minutes, we're going to talk you through our process of finding the solution and why we're really excited about finding solutions for this challenge that we've undertaken. So let me kick this off with a question. How many of you have or are planning to get a pet? Interesting. Unfortunately, there's a bit of sad news that I have to share here. Earlier this year in August, it came to light that a lot of pet owners, they embarked with their pets out on a mission to explore the wilderness, but unfortunately they had to return home without their pets. So these pets, they played in the water, which had algae, which sort of, they weren't, the pets didn't do so well. Well, let me sort of change the topic here. How many of you guys like to go hiking? Interesting. There's something that not a lot of us think about when it comes to hiking. A lot of these stagnant water bodies, such as ponds, lakes, these stagnant water bodies have algae, and these algae contain a microsystem. This is really toxic and can cause harm to human livers, can cause harm to pets and whatnot. So our solution is AccuWater. It is an app that we've built. Just like you check AccuWeather, you can check AccuWater to determine whether a water body is not contaminated, whether it is safe to venture into there with your pet. So let me walk you through the app while we probably tell you a little more about our solutioning process. So it's a pretty intuitive app, and we've designed it in such a way that the top right corner is color-coded and has a number. This number that you see here, this 75%, is a sort of aggregated score that we've managed to calculate, and this gives you the safety percentage of the water body that you're planning to visit. Now, we've built this in sort of an intuitive way, such that people with, some people even without a lot of digital skills can look at the app, can look at the color codes, and can figure out whether it's safe to venture out or not. Now, we've got one step ahead by using machine learning models to predict whether a water body would be safe or not in the subsequent days. So let me quickly walk you through. This is subsequent days, where you can see that it's color coded. So green means safe, red means danger. Now, there's a lot of other data that we have displayed here. We have seasonality trends, we have individual parameters, and one other interesting feature that I'd like to share with you here that we have conceptualized is a map overlay. So just by looking at this, we can get a sort of overarching view of the water bodies around us and can see which water bodies are potentially unsafe or safe. And by just clicking on the blob, we can get data, immediate data that is shown to us.
We have 1 minute for judges' questions.
Where are you pulling all the data from? Where's the rest?
Question is, where are you pulling the data from?
Sure. So I actually missed that out during the presentation. We use data from MODIS satellites and specifically IR data. So we experimented with a lot of data and we spoke to a couple of experts to figure out that IR data sort of gives us the most accurate prediction rather than using images. And we used that data and applied our machine learning techniques on it.
Thank you.
Any other questions?
What do you see with the IR data?
So with the infrared rays, we accumulate parameters like temperature, wind, chloroform content, and chlorine content of the water pigmentation. So we collect those data and we evaluate those parameters to build forward our machine learning models and to predict the results.
So you create a vector into the model and it gives you a score back?
Yes, we use regression model. Any more questions?
So these are sort of some of the parameters that we were discussing. So we have organic carbon, nitrogen, microcystin, and others as well that are visible on the other display with the green, red, and orange visual. I can pull those up as well. So these are some of the other parameters. We have turbidity, we have temperature, and there were a lot of others. We sort of narrowed them down to a few that users could actually see and empower themselves with information quickly.
So you have a lot of parameters here that you're aggregating into a single safe, not safe.
Yes.
How did you decide how to aggregate them? What was the approach taken?
We will take that.
Yeah, sure. So there were two things involved in this approach. First, we found out the correlations, and we also used research papers which were already giving us the research that they are affecting the values, and so we decided to take all of these into consideration.
Just to add on to his points, there were research papers that we found that were doing this study, and they had mentioned a lot of parameters that were key in their study. So we built upon that, and we sort of figured out which of these parameters are key to predicting algal growth in these water bodies that we just showed you.
With the highest probability.
And so our solution here was sort of getting the information to the end users who might be tourists, pet owners. That's sort of our solution, because all of this data is in like the raw format from satellites. It's not really accessible, especially at your fingertips. So that's sort of where we built upon existing research, applied some of our own models, and came up with the solution.
Thank you. Okay. Next up, Team Rip City. Rip City, you are up on deck. Nathan.
building is on. They're working on it.
Hello, everybody. How are you guys doing? So we're Team Rip City. Can you guys hear me all good? Cool. Thank you. So we're Team Rip City from Portland, Oregon. Oh, I need to get my notes. And let's go to the next slide, please. So we're working on the Spot the Fire Challenge. And who are we? We're from Portland, Oregon. Just like I just said, we really care about nature, conservation, and safety. So the context to what we did today is there's a lot of data everywhere, and especially for fire data, there's data about people taking pictures, data from NASA's sensors from the satellites, but there's no real way for people to understand if I am at risk or not, because we researched how the California notification system works for alerts for wildfire zones. It's just a text message, and they have to every day look at the weather news and understand, okay, how are the winds like? How are they blowing? Where's the fire at? Am I at risk? Am I not? How should I prepare for this? And that's a very big deal because this was a big problem. Lots of zones that were not deemed to be in risk were actually under fire this last year. And this is a big problem that we're trying to solve with our app. So yeah, I think I explained everything. Let's go to the next page. So our solution takes two parts mainly. So there's crowdsourced data. So there's a lot of people with a lot of great sensors, that's their phones, taking pictures of things all the time. So let's get this data, use that, coupled with data we know what is true, which is the NASA satellite data. Those are going around the Earth, looking at pixel by pixel, 1 kilometer square areas of the Earth, and with their complex models predicting if there's a fire in that area or not. So we have the data from the NASA models. We added the ability for people to get pictures with our trained models, detect fire, and see if those are accurate. And coupled with all this, we built an app so that's simple to use and people get a better understanding of are they at risk or not. So let's give a quick demo for our app. Let's go. So like I said, we want this to be easy because many people, even though we're very technically capable, most people are not yet because this has been a very drastic change in technology. So the first thing is we have a map. So we have the entire map of USA if you zoom out, or the world, but USA. And this is all the red fire dots that you see are coming from the NASA satellite images that are deemed as fire risk zones where there is a fire right now. So we can zoom into one of these zones, and here we can see that that's a very high risk zone for wildfires. And this is coupled with the data that people have provided. So there's someone here that gave a picture of the fire. And so that's our map page, which aggregates this data, and people can upload. So we have a reporting page. And this is where it's a simple way for people to click pictures, upload it to our website. Very simple. Just one click, done. And then the next page is the prepare. Let's go to the prepare. We're running out of time. So the last page, the goal of this page is to give people help and links to understand how they could protect their own house, rake their leaves, clean the debris and everything so that their house is protected, and how they can be ready with like supplies and etc. in a time of need. So it's not beautiful yet, but it will be, I promise. And we will deploy this to the App Store. So thank you so much. This was Rip City. Any questions?
So you're taking data from human beings about pictures and whatnot. How do you validate and crowdsource that data in a way that's appropriate to really correlate it to where the fire actually is, and that it wasn't taken some other place, or those
Yes. So we use the geolocation API from the picture. So every picture, when clicked, the picture itself has a geolocation tag about the coordinates of the picture. So that's how we get the data for the latitude and the longitude for the picture. And coupled with that, we have our machine learning models, which are not great right now, but they will be. So we get we get a decent classification rate right now, but because we're not really getting a great classification of is this picture of fire or not. What we did is that multiple sources, it's kind of like ways where multiple people can say, oh, there's actually a cop here, or there's actually an accident here. So as more people get their data sources there, we know what data sources are more accurate or not, because that's how there's more circles here, which tell you if there's actually a fire or not. So that's the goal of the idea. With more data that people can tag, and the crowdsourcing efforts, so they understand the neighborhood around them and how it's changing. Any other questions? Anybody from the audience? Thank you so much.
Thank you, Team Rip City. Team Maven, come on up. Fire in the sky, you are on deck.
I see, so you can cover them.
Well, good morning. I want to thank everybody for being here. We are Team Maven, and we decided to also take a look at the fire in the Scout but we want to be able to spot that fire, version 2.0. Fortunately, we took a slightly different tack, and the previous group introduced the problem, so anybody need help spotting the fire? Just want to make sure you can see it. So our approach to the problem, or the problem itself, was to say, look, we need to estimate and predict actual fire trends. We also want to use current information. We want to be able to make predictions. But specifically, one of the areas that we targeted, we said, okay, let's start building our own rudimentary model. And we'll talk about why actually modeling is important in this particular case. But we want to say that the app that we were supposed to build as part of the challenge is just sort of part of that system. But we focused on the model in this particular case. So that was our goal, was to make a model. And so that's what we did. So the data sources that we used, there's a ton of great information out there. There's maps with a gazillion layers already on them. A lot of the data is already available, and some of it's even aggregated. When we say, hey, go to firms if you want to be able to see aggregated data that's going to talk about the basic components of a fire, it's there. And honestly, it's fantastic, and there's no point for us trying to reinvent that wheel. But we did want to say, okay, let's start looking at the basic components of a fire. We know that you need heat, you know you need oxygen, and you know you need some kind of fuel in order to get that whole cycle going. So we're going to take a look at two parts of the problem. One of them is the radiated heat aspect of it. So that's the part where it's actually hot, it's burning, and it's moving out. Well, that's good. But there's also the winds. And the winds, of course, when a fire is very small, they may sort of help a little. And it depends on what you refer to as help. Helping could be making the fire stronger, hotter. And indeed, when a fire has actually gotten to a certain temperature, that's exactly what the winds are doing. And so we realized that what we're dealing with is actually a really gigantic weather problem. It's a convective activity problem, except instead of rain pouring down, you have fire that's burning up. So this is quite a significant challenge. And to use modeling for that in the strictest sense, or like machine learning, without incredibly accurate detailed data is going to be a difficult thing to do. Because the bigger the fire gets, the higher the levels of winds that are involved in actually feeding that fire. And as those winds descend, they get drier, they get warmer, and then that warm, dry air is now available to the fire that's getting ready to burn. So it ends up becoming something that sort of feeds itself, and it's not restricted to the low level winds. It's the upper level stuff that comes down. So we built, and we started with a very simple model. We have a little pixels. We have show a heat map moving out. What we want to be able to do, thank you. Want to be able to have the winds blow over that. Then we'd also like to be able to, expand that into a three-dimensional picture. Once we do that, then we can actually have the convective activity as it's occurring going up to those three-dimensional layers. And here, at least, is our 2D visualization of that heat spread. So we're able to get this far. We like it. All right, but of course, eventually we get to the point to where we say we need more data. That was AWS IoT, and IoT is going to be the answer. We realized that there are cheap methods of getting sensors in the right location because being able to model something is not necessarily great if you don't have incredibly accurate data. So let's take some of those, let's harden them, let's put them in there, let's do it for recovery and post-fire analysis. More sensors, more data means more accurate models, especially if it's a very localized weather phenomenon like a fire. It is its own weather thing. It's doing something that's very different than what we normally understand.
Thanks. So you mentioned that this is part of a system of systems.
Yes.
So can you tell me a little bit about what ideally would be the systems that would interact with this, in addition to sort of moving beyond your sort of the IoT system of sort of cheap sensors that you were talking about? What would be the other systems that this would interface with, and what would it look like when it's really singing?
Okay. So as you could, so in addition to like the firm's system itself, which is, yes, there's a lot of overlays, but there's two components. Do you know what's going on right now, and do you know what's going to be happening in the future? Do you know what's going to be happening in the future close enough to a point where you can start to alert people in the right areas? And so that's where the simulation and modeling comes in. When this is really working, you have things like WonderMap, you have things like everybody's cell phone. And UW actually has an app that gives pressure. If you download the app and you just use it, but you get pressure measurement for everybody all over, wherever. Everyone who has the app is a pressure measurement. And one of the more significant parts of weather phenomenon and everything else is, do you have an accurate pressure map? Because that's going to drive winds, that's going to drive that. Basically, it's just part of the whole thing. So when this is really working, you've got data that's being integrated from everybody who's got one of those little things that's connected to Wi-Fi attached to the house. It's got every cell phone that's providing that, accurate pressure data, and it's the sky's the limit, I guess. And IoT is practically everything. There's no limit to IoT, honestly. Because everything's connected and it's sending data of some sort. So to get right back to the point, the device that's in my pocket that I can't get to is not only giving me the warning, but it's also providing the information back to the system that needs to get it in order to send the next accurate notice to me and to whoever else is around me. And that's really when it's working. Sensors are, it's never a single purpose thing. It's sensor and warning device.
That was Team David. Fire in the Sky is up now. After that, we'll have hot water. Hot water, please get in there.
So normal people don't really feel qualified to have an opinion of global warming or to think things like sea level rise. How do you know if you're talking to a normal person? You walk up to a normal person and you say, how many people have been to Mars? They will tell you, I have no idea. That's a normal person. We're not normal. So what we want to do is figure out how do we reach normal people so they can become more educated, have the ability to talk about climate change with their friends, people they relate to. We thought about a few different ways we could do this. One of them was through graphical visualizations of some of NASA's data. Another technique we thought about was let's show them topographical maps of what different parts of their local community would look like underwater. Let's develop a video around a touch and feel kind of demonstration, something physical that you can touch. People like to touch things. So we thought we'd bring this device to visual aid to trade shows or things like that so people could actually experience it. And we thought we'd put all this stuff on a website so other people can find it and maybe borrow from our ideas. So quickly, sea level rise is caused by two effects. One is ice. This is a histogram showing how much water there is at different places on the Earth at different elevations. A lot of the ice will melt and go into the oceans. That will rise the sea levels. And also the oceans themselves will expand as they get warmer. As their volume increases, that'll push the water up onto the land and help float the land. Next slide. You get something like this. The two effects combining cause sea level rise. So how do you communicate that? We wanted to make a visualization. Let's go to the next graph. Where we actually have a line that moves in time. So we go from present to the future, say 100 years in the future. We can actually see this line change and see the water redistributing. And we actually use NASA data to create this line today. The thing we observed that was really interesting was how much land there is that's close to sea level. You can imagine if all this volume of water over here expanded a little bit, it would quickly flood a lot of the land. The enormous amount of land is very close to the sea level right now. We also wanted to produce topographical maps. So we created these maps, but we flip through them to give people a sense. These are designed to show how the water is moving across. In this case, we chose Manhattan. It's a little hard to see, but that's the idea, to develop these maps and get them for each community. And lastly, we produced an actual physical model that people can touch. You have that model handy? Ooh. And we created a video around this physical model, which we're going to show next. We actually put a block of ice in the model, hit it with a blow dryer, and watch the ice melt. And you'll get to see that next. In theory. Oh, yeah, slide it over, yeah. Slide it over. I'm going to slide this, take this and drag it over to this screen. Cut from the top. Hold it. There you go. There you go. Let me put full screen on. All right, we'll start the video. This is a laser cut. You want to talk to this?
Yeah, sure. So I vetted some of the Seattle makers. I went over there, a member over there, and I used the laser cutter, dropped in an image of Manhattan, and laser cut out a scale replica, hit a block of ice or our glacier, polar glaciers, and with the heat gun, and then melted over a time lapse of around 10 minutes I sat there. So yeah, it turned out pretty great.
So you imagine if somebody had a booth and they had one of these little tanks sitting on the desk and they had a block of ice in it. Lots of kids and people will come over curious and ask them more about what they do. Thank you very much.
How do you keep your physical presentation from just being sensationalistic rather than make it more accurate as to showing what sea level rise would really be? Is there a certain amount of ice that you would have to put in there to show something realistic rather than, oh, look, it's flooding because there's a giant block of ice that's 1,000 feet tall?
I don't think that particular demonstration is meant to be, represent accuracy, but it's supposed to be people engaged in conversation. So you don't stop and you wonder why there's a block of ice in this thing. You start talking to somebody and learning more about it. And that's when you get exposed to the real data and educated on what's really going on.
What motivated you to go for a physical demonstration as opposed to a VR approach or some other approach to visualize what the sea rise example that you're showing?
So we started with a kind of a customer first approach and asked ourselves, what would people want to see or learn? And from that, we got different opinions. Different people. I was personally attracted to data-driven type stuff. I wanted to see a visualization of data. But other people thought something more physical and hands-on would be more engaging. And so we said, let's just try them all and see how it works.
I also feel like we're living in a social age right now where social media influencers can have a big outreach more than our typical scientific community can sometimes. So I think being able to speak out to those people that they can then spread that information in a way that maybe reaches out to those people in particular that we aren't being able to touch, I think is maybe able to touch a much bigger community than we have before. So.
Time for hot water. Hot water is up now. Lakeside, you are on deck.
Hi, our team is Hot Water, and the challenge we decided to take on was rising waters. Currently, 40% of the world's population lives on coastal cities. That means approximately 3.1 billion people will be impacted as sea levels continue to rise and push people out of their homes. And so, with this information, our team wanted to create a visualization tool that helps inform the public about the impact that rising sea levels can have on our communities, because it's not extremely obvious, because rising sea levels is a gradual problem that's happening and it doesn't have any immediate impacts. So in this picture we have right here, this is in North Cove, Washington. So we can see that rising sea levels are already having an impact in communities local to us. And it will continue to have an impact on local cities on the coast. So for our tool, we utilize Google Maps and Google Elevation APIs so that we can calculate elevation levels of cities on the coast. And then we use NASA data of sea levels, carbon levels, and temperature to try to capture what sea levels will look like in the future and simulate when our cities will start to be threatened by rising waters.
Yeah, so we looked at some of the data from the NASA website, and first we looked at the sea level over time. This is just the independent variable, and we find that the sea level rises about 3.3 millimeters per year, and the sea level is only available since 1993, but we have the other data goes back much longer than that. Yeah. So this is the temperature of the ocean water since 1980, and we've also modeled the data since 1993 later in the talk. So we're looking at the effect of carbon dioxide on the sea level. So the carbon dioxide is again one of the things, in addition to temperature, that has a correlation with the sea level, and you can see from this graph that indeed, as the carbon dioxide level goes up, it's in parts per million, the sea level also rises. And then we do a model for predicting the sea level from carbon dioxide and the temperature of the water and the time, the years. And that's what the predicted sea level looks like.
So we understand that rising sea levels isn't something just local to us. So for us, our goal is to create a model that is able to represent the whole world so that people throughout the world can accurately see when they will be impacted by rising sea levels, because this is an issue that will impact our cities, our wildlife, and our forests throughout the world. And so to do that, we want to be able to use data, current data, so that we are always having our accurate representation of what the sea levels, the state of the sea levels on our communities are presently. Thank you.
Could you elaborate a little bit on what the state of your app is? You mentioned an app with Google Maps API.
Yeah, so we were using Google Elevation, which provides elevation data of cities on the coastal area. And so we wanted to use sea data from NASA that we use the level of the sea to kind of find when this sea level will overtake the elevation levels of the cities on the coast, and then we want to create animations to represent or show how and when this will happen.
Did you guys get a chance to look at other sea level increase models, and how would, you know, in a best case scenario, how would this sort of interface with some of the models that are out there?
We use just a linear model for this, and we did look at some of the other research, both from Washington State and local, which use SEMs. I didn't read the whole article, but I am a statistician and I could do that, but I didn't read it.
Thank you. Lakeside? Come on up. Ocean Roomba is going to come up after Lakeside.
Hello everyone, we are the team Lakeside and we are the UW students majoring in computer science. So this visualization project is based on rising water. And people always talk about environmental problems and they always serious about it. And we just want to show a specific aspect to the problem. So this main consideration of this project is to visualize the changes of sea level from year 1993 to 2019, as well as the other environmental parameters, such as the concentration of carbon dioxide, environmental temperature, and the surface of the iceland in the North Pole and South Pole. So my partner is going to talk about the project we are working on.
So this is our website. If you forget which year it is now, you can go to our website and it shows 2019. And what's more, it shows the world now. This is our world. And it is too hot now, so the sky becomes red. And the sea level is very high, 52 millimeters. And there are lots of annoying particles here, means carbon dioxide. So this is not good work, so we're about to take a time travel. Use this time machine. Whoa. So it become better now. Why? Because we connect the temperature to the color of the sky and the thermometers, obviously. And also we connect the data of sea level to the sea level. And the number of particles means the number of concentration of carbon dioxide. So we can go all the way to 1993. So now the air is very clear now, and it's very cool now. And if we go back to 2019, we will find a very big difference. And if we click the button here, we can see all the data here. So it is a simple website, but it is very directly give our idea to the audience. So we want every people come to our website, have a very deep expression, and we will remember it all the time. So whenever people say climate change is nothing, they can go to this website. And we show it, whoa, So it's very obvious. So we do not want a lot of different graphs, different charts that are free-running. We just want to show the data very directly. Yeah, that's all. Thank you.
Hi, thank you for the presentation. Can you explain why you went back to 93? Was it based on available data? And can you also explain, did you consider going in the future with predictive data?
Yeah. So the data was back to 1993 because we only found data on the NASA website dating back to 1993. And the motivation or the intuition of the project is to discover a relationship between now and the future and find the connection of the variables to the future climate. The idea is very good, but we don't have enough time to work on that part. So that's all.
If you did have another year to work on it, what else would you add?
Yeah. So if I have time, we like to use some machine learning technologies to process the data. So the data it's pretty much I download from the website and I simply get the average of it. So I only use Excel to process it. And so if I have enough time, I could discover the data using machine learning, and we can add more variables such as the human population, the temperature, and some other parameters. So with all these parameters and the effort human made, so what will affect the sea level or the environmental problems? Thank you.
Ocean rainbow. Let's get sweet. On deck, 5 people.
We did the ocean Roomba. This is Kaden, CJ, I'm Zach, and this is Leo. And if you can't tell, we got like a Roomba sort of cleaning the ocean.
Okay, so pretty much every year we dump something like 7 million tons of trash and like mostly plastic into the ocean and causing very serious problems on the environment. And then so those tiny particles of plastic can be mistaken as food by the birds and the fish and ultimately go into our body. So there's going to be more plastic than fish by 2050 if we slow in taking actions. So it's very difficult to know where is the plastic because the ocean is very big and the plastic, especially the small particles, are very small. So the plastic has a footprint in the infrared light, which could be leveraged to be detected by the satellite. But since this technology is still at the very early stage and requires a lot of domain knowledge, and we decided to pivot to something else that's doable in 2 days by looking at the natural disaster, how does that impact the trash? So so the Japan tsunami in 2011 washed off about 20 million tons of trash into the ocean, 3 times larger than the annual dumping. So in normal times. So we built a web app show you how the trash is going to be distributed nearby the Seattle if there is a tsunami is triggered.
Okay, so I'm their tsunami guy. So since we want to, we think like if we can simulate the tsunami wave, maybe we can find out where those trash goes. So here I use a very robust model called Comcat, and it's very complicated. I don't want to talk too much about that. Only thing you need to know is this model can simulate the initial tsunami wave and the wave propagation, and you can also calculate the inundation things. It's very cool model and very reliable and accurate. Yeah. And so we need some data from NOAA and USGS. We need the bathymetry, and we also need the earthquake parameters. Then we can put these parameters into our model. And our model can give us some information about like the maximum tsunami wave arrival time, and tsunami gauge data. And then I create a scenario in our Cascadia subduction zone earthquake to simulate a tsunami. Yeah, and I pass the data to our web app magical guys. Yeah.
Okay, so my job was to take that data and to make it more understandable. And so it's kind of a heat map that's integrated with the Google Maps API, and the red zone means it's a higher energy potential of the tsunami, and then as you can see, the blue ocean is where trash basically wouldn't be. So.
Yeah, looking towards the future, we sort of want to use this technology and use infrared to figure out where the trash and garbage is in real time. And that'll sort of give people a better idea by looking at our application where the garbage is. And then we want to actually use that to track where garbage is coming from. So if it was coming from like a natural disaster or something, we'd be able to track where the trash might be using a model. And you could also use such as rivers or streams so we could sort of find the source. And yeah.
So I had a question in regards to these microplastics that are out there in the ocean that may not be on the top level of the water. How far low can the IR actually pick up these microplastics in the water themselves as a real-time detection method?
So based on so I'm not an expert on that, but I read something just yesterday. So it cannot go very deep into. So most of it is still very close to the surface of the ocean. But there are more garbage under the water. So by looking at the thing on top of the water, we are seeing the tip of the iceberg. So that shows how serious the problem is.
So quick question. So who would use this and how would it change their behavior?
So this is going to be interested by the general public, whoever are concerned about our ocean, and also can be used by the scientific community. So we hope to have a very fancy web app to continue to show you where is the trash. And then also, if we figure out some way to clean up, then we can also to reduce the density to show how is our effort improve the condition.
Okay, 5 people. 1, 2, 3. Ooh, that's an interesting.
Explain it later.
Okay. 5 people is up now. We're moving the order just a little bit. Ergo, you are on deck, and you will be followed by handy people.
All right, hi everyone. So our team name is 5 people, but one of us had to do homework, so he couldn't show up today. All right, anyway, so our project name is Project Mothership, and the challenge we took on is trash cleanup in the ocean. So the problem. So over the years, there have been accumulation of garbage in the ocean, and there are 5 major patches in the world's oceans, and we were able to figure out how where they are using NASA's data on ocean currents. And we decided to work on the Great Pacific Garbage Patch, which is between Hawaii and California. So that's our main project. So a little bit about the Great Pacific Garbage Patch. It's estimated to be 80,000 tons of buoyant plastic, so that's a lot. That's equivalent to 500 jumbo jets, the weight. And there are about 1.8 trillion pieces of plastic in there. And most of it is like microplastics, which can enter the food chain if swallowed by smaller fish. So that's a pretty big problem.
So this is like the 3D models that our group made using SolidWorks that I made it personally. So before going into the 3D models, so we're gonna track the garbage on the surface of the ocean by using the NASA data, which we call MODIS, moderate resolution imaging spectroradiometer, but on the surface level. So it captured the image of the surface current on the ocean around the world, and we kind of predict how the water flows and converts at one point and pinpoint that into the location. And the idea that we propose is that we're gonna send this one big ship that we kind of name mothership that contain like several small water drones like here, and it's gonna collect the trash on the surface of the ocean and then bring back to the mothership and sell back to the ground and then sell the plastic that collected to the recycling company. So this is like a more detailed view, the 3D models. Well, it's not really, it's just a prototype, so it's not really research on how the fluid goes into the robot and it can make it float or not, but just the basic idea. So there is the isometric view, you can see that. And the second image on the bottom is like the top view. And it's the section view when you cut the drone into half. And you can see that if the trash is kind of goes from the mouth and it goes to the back, and we're gonna kind of attach like a net on the back of the drone so it kind of collect it and it kind of bring back to the main ship. And it's like the gear of the conveyor belt.
So I designed the software to monitor where the mothership is. So if I click the name of the mothership, I can see more information.
Okay, so the challenges of the project is that how do we manufacture the drone by environmental friendly setting, like using the recycled plastic or maybe using some used rechargeable battery, and then how do we ensure that the water drone doesn't disturb the marine life, such as like maybe we suck some little fishes into the net, or maybe some the sonar and what the control disrupt the communication between the fishes, such as like dolphin or whale, and then how do you like make sure that the efficient of the project due to the search of the garbage trashes, because the some plastic can be like very low.
Thank you. So what made you guys decide to go with an air-based platform versus a water-based platform? What were some of your design decisions?
Actually, the wing is which our design is based on water based, but we just make that wing so that it can stay afloat and not be disturbed by the water current.
So I didn't understand, how does it segregate as it's scooping stuff up? How does it segregate between plastic and intelligent challenge and marine life? But it could be anything, it could be rocks or sand or anything.
We plan to kind of use infrared sensor to differentiate between plastic types, and also we try probably like some of the idea there out there is that make it so enough so that it will not the fish will have enough time to go.
Did you do any high-level analysis of how much garbage your system can collect and how quickly?
Technically, we didn't go into there, but we kind of think about it, but we decided to like not really go into it because of the time constraint that we have.
Okay, Team Ergo. Ergo, you are up. Handy people, you are next.
I hate mics. Mind if I don't use it? Here you go. Okay, I'm Jeff Zika, Dylan, Heroes in the back. Team Ergo, this is my company, so effectively, excuse the plug. Now why is this not working? Okay, hang on a sec. My laptop just locked.
By way of introduction, we were working on the Out of This World challenge, which applies to remote control, intuitive remote control of drones requiring manual override at a distance. In particular, I was looking at, and we were looking at time delays that would make it impossible to utilize intuitively an acceleration-based control in the manner of a cell phone tilted like a marionette. To that end, we developed a mode of crawling locomotion and a peripheral, essentially a 3-axis mouse for that purpose. That's
one of the things we worked on, but that's not the primary reason we're here. The primary reason we're here is develop an AI for remote monitoring of autonomous systems that can take control. Autonomous is still autonomous control, but remote control of a system in a fault, in an autonomous fault. Continue. We can work on Earth, on Mars, for autonomous exploration UAVs. These are some of the landers that are some of the devices that are currently being developed by NASA that are being sent to Mars in the near future. A concept, centralized intelligence for the state of fault monitoring of autonomous systems with remote operations capability. In use cases, remote control of anywhere UAV operating in an environment that defeats autonomous operations, urban canyon, bad weather, so forth, where fine control is required. Autonomous system failure, sensors, autopilots, wears. Manual control in key portions of flight, for example, landing in an urban environment, navigating tight terrain, so forth. And remote alerting and control if onboard pilot. This is future for autonomous aircraft or pilot option aircraft if the onboard pilot is incapacitated. What we have 2 control systems. There are multiple control systems, multiple UAVs, okay? With a centralized AI that monitors everything that's in flight or in the area. They can take control at any time if required, or send an alert, or monitor alert. Work to date, we've done remote streaming via the UAV, remote control ground telemetry across the internet for over long distances. Prototype aircraft is built and in testing as part of our prototypes, and ground control system using mission planner control. Control is tested, and we're continuing development on top of those platforms. To do, get a little bit of a view of what's going on. This is actually a remote camera that is positioned in the back, attached to another one of an NVIDIA Jetson like this, and that's Hero. Okay. Okay, to do is develop remote reinforcement learning system and training for remote autonomous control. Right now, focusing only on Mavlink control of any type of UAV. Refine control system to work with any Mavlink compatible autopilots. Developed reinforcement learning system to act as an immediate remote pilot. We need more development on our vision systems. You can see some here. And control algorithms. Start with the technical difficulties.
So could you just elaborate a little bit on the 6-axis gyro sensor and how you're using it?
To be honest, we're using an autopilot that's pre-defined off the shelf, and we haven't been using the 6-axis sensor of anything. Our standard control method is still RC. Our backup revision control method is via ground control station, and the AI talks to the ground control station through ROS and Mavlink.
Do you see this system as being part of the NASA research project on UAS, traffic management, or UTM systems that's going on right now?
We're actually involved in that project. We're involved in the Grand Challenge and several other parts of it that relate to the Grand Challenge for developing UAV and pilot optional collision avoidance systems. So yes, from a computer vision perspective, yes, it will be involved. From a control perspective, I can't say.
The data that you're using, is it all from your drones or can you pull external data into?
We can pull data from anyone. As long as it's accessible on the internet, or if it's accessible via any kind of telemetry link that we have access to, then we can pull from it. Right now, we're using our own data, and it's via custom telemetry links, our telemetry links. This particular version, which I built this weekend, is Wi-Fi enabled, so we can work with anywhere there's a Wi-Fi signal. It could be on the other side of the world, and we still control it. And still pull data.
Awesome. Handy people, come on down. Seattle Falcons, you are on deck. And guess what? Once we hit Seattle Falcons, we're on the halfway point. Okay.
Hello, everyone. We're the handy people, and then today we're talking about the challenge from Curious Mind, Helping Hands. So for the design, we basically built a WordPress, and it's hosted on AWS. This is a platform would be used to share imagery from the satellites and share around the world. Everybody with internet can access it. So here we're trying to use a satellite imagery from NASA, and then this is one of the image found from the social economic data was from NASA. So we did some image processing on this one, and then you see we put it on top of OpenStreetMap. We can see where the fresh water is actually located. And for next, we have another OpenStreetMap. This is for Africa, Niger. You'll see like this area is pretty brown. It's like it doesn't have any water in their rivers. And then next is the vegetations as well. We don't see much of a vegetation plants being grown in this area as well. And this type of work can be, this image is actually like global wise. So if you're interested, you can always like look around in different places in the world. Yeah. And the future challenges.
So as climate change is happening, dry area will be drier and wet place will be wetter. So for the future work, we wish to utilize machine learning algorithm to study these satellite images and integrate them with the emergency drones that deliver medical supplies to first response to clean water. And also we wish to create an disaster notifications app like UW alert, those kind of things to send text message to the emergency center for help. Yeah, that's our plan. Thank you.
Can you give me an example of what kind of machine learning algorithms you would want to use in the future?
Well, for vegetations, we can use machine learning to find out which part of the world requires more attention to, or we need to pay more attention to. So like we can use like color, we can use other sensor data, and then we train using like neural networks to on the images.
Could you be a little bit more specific? Like how would you score those models to make sure that they're actually giving good output?
Well, we can compare data from a few decades ago compared to now. we'll assume, like, let's say like 20 years ago, this place is actually flourished with like vegetations. We can compare our current data with that. And I think that will give us a good representation. Anything else? Thank you.
Okay, Seattle Falcons are going on now. Data for Good, you are up next.
Hi, good evening, everyone. Thanks for taking time to listen to us. We are called Seattle Falcons. It's the Rocket, by the way, not the other team. We have taken up the challenge, the Curious Minds Comes Helping Hands, and our product name is called Digital Wellbeing. About us, we are a team. We all work for the same company, and we have a passion. We are passionate about building applications for the betterment of the human beings. And we have similar skill sets. We complement each other. We heard about this hackathon, and we thought what better way to spend the weekend with curious minds like all of you. We are happy and excited to be here. Our challenge that we selected is the Curious Minds Comes Helping Hands, and we use NASA resources to attempt to solve the problem. So a little short history about why we choose this problem. As I said, we want to help the humanity have and arm them with better information to take their decisions. The data suggests that 25% of human deaths are because of the natural hazards. And the hazards range from cyclones to earthquakes to flooding. For this particular problem, we chose just the flooding hazard to incorporate into the model. And then later on in the future, we're going to expand the model to include dynamically the other hazards as well. So that's the why behind our intent to select this problem. And while solving the problem, we selected a small geography and started to overlay multiple maps in terms of, we started with population data from the NASA data websites. We overlaid that with flooding information from another NASA data website. We converted the raster images that we had into vector formats so that we can come up with the dots on the images. And because the raster image is more heat map kind of information, because the vector was more pointed, and we had to convert to that to represent the population data. And that is how we overlaid the population dots on top of the flooding information. And our intent was to show the color intensity shows the higher risk associated in that region for that population. Do you want to add anything to that?
Yeah, so actually, the higher the intensity, for example, the red one, right? So that is, basically more flood hazard possible, impacted area in the future as opposed to the population. So that is what we wanted to highlight by the different color sets and shading of that.
Sure. Yeah. I briefly want to talk about our journey, which has been very great experience for us. So we started with the CSV files. We explored a lot of data. We were overwhelmed with the data that we found out on NASA websites. We wanted to use the CSV files and represent it on Tableau, but then later on learned about a lot of formats on the rasters, the HDF files, and the TIFFs, and we pivoted our solution to use the QGIS tool along with the GDAL libraries. So that's been our journey, and that's how we produce the output. And in our future enhancements that we plan to do are, we want to dynamically include whatever hazards are available out there. We want to provide a chart that with the checkboxes for adding hazards dynamically. And we want to provide a platform where that testing can be done
Hey guys, I had a question in regards to, you talked about flooding and then you talked about kind of areas that were more likely to flood. Did you guys give any consideration to who may need the most aid in those areas as well as a risk profile? Or is that something that could be potentially added to your models?
Yeah, we do that. Actually, we want to concentrate on the, like, say, like schools. That's one of the where the people, the kids are there, so they need the attention in the first time. And we are also concentrate on the age, the sex, everything. So right now, the future is our scope of doing that. So as you asked, yes, we did that. We considered considering other demographics like male, female, and the ages of it.
Okay, thank you, Seattle Falcons. Time for Data for Good. SD Gensi, you are on deck.
So hello everyone. So we're more than halfway through the presentations. Any guesses about the winners? So we did Data for Good, and we've chosen the task of Rise to Resilience. Basically in this task, the regional green engineer has to develop a green sustainable infrastructure, and that's the biggest challenge. So before we go and find out solutions for the challenge, we need to figure out what the actual problems are. And for that, I'm going to show you a few graphs. We have calculated this, we have analyzed and visualized this data using NASA data sources and other sources as well, the external ones. So we have average daily max temperature from 1950 to 2019 actually. And then we actually also compare the counterfactuals and get a peek into the future temperature as well. So we see that the slope is actually rising, which is scary, which is something to be concerned about. We also came across total precipitation against the same time variable on the x-axis. So I just had one question. How many of us actually care about the environment or the climate change here? I guess a lot of us. How many of us actually take proactive measures to change that? That's good actually, but not the majority of the room. So this is actually where we plan to come in. We try to build a creative prototype where we bring in all of us, and then she'll explain how it goes.
Okay, thank you. So I'll quickly try to explain what we as green engineers think that the solution might be. So, okay, let me explain this really quickly. So Washington has 39 counties, okay? Now, because we just had 2 days, we'll focus on one county for now, and that is our King County. So what we did is we used NASA data and we used machine learning algorithms to predict what or to analyze what kind of problems each county has. Okay, so because this problem is so huge that not just one community or one group of people can solve it, we all together have to come and that's for the greater good, right? So we try to we developed a very interactive platform where users have that, like, we will give the transparency to see you give users the transparency to see all the data that's available, where we stand right now, what is the water pollution content right now, what's the air pollution content right now. So users know, okay, we are in great trouble. So that's why, so this is a basic website. This is our user data, user homepage. So see, what has happened is we are right now here with according to global warming, and what will happen in the next 50 to 80 years, given the conditions right now, and that's pretty warm, right? I mean, we are in deep trouble. So the thing is, what should we do collectively as people? And that's when we talk about many problems that affect each county. We've discussed some like air quality, water management, go green, garbage disposal. Some solutions might be okay. So for go green, we can cut plastic use, we can plant more saplings, trees, etc. So in this approach, we as green engineers uh, give we as green engineers give all the okay, I'm getting very nervous because this is a 30-second timeline right now. But yeah, all the users, one task per month. That's it. So 22 million people in one county, and imagine just one task per month. What can you do? So see, carpool today. Okay.
Hi, thank you for that. Glad you recovered. That was great. Can you talk about some of the solutions that you explored? So carpooling is a good one, reducing use of plastic. What are some of the other solutions that?
Yeah, I would want to highlight that. For air quality, we said that we could reduce carbon footprint, go carpooling. Yeah, also for water management, we could take up initiatives like rainwater harvesting. For go green, plant trees, cut down on plastic. For garbage disposal, you could cut down on the food plastic. Chimney sweeping and keeping a note on how much is your garbage count. And these are some basic tasks that we actually want to give to a user or the citizen so that they don't feel compelled like, oh God, we have to do so many things. They just have to do one task, 1 month. And considering the amount of citizens we have in one county, we can make a huge change. It's going to be very cost effective, and I believe this plan is really good.
Also, one thing I would like to add is that this task is specific to one county, and that depends on the problem which the county is actually facing. So every county will face different problems, and those citizens will get a specific task. So yeah, actually.
Thanks so much. Okay, you know what? Since we're at the halfway mark, let's do this. Everybody stand up. Stand up. Stretch. Reach for the stars. Twist. Turn yourself like an observatory, pivoting towards Orion. Okay, now everybody drop on the floor. It can be mountain climbers. All right, never mind. Let's sit back down and get ready for the next set of presentations. SD Gansey is going now. No logic. You are up next. Bathroom break? Okay. Judges call a bathroom break. Go for it.
Are you guys in contact with Paris? Are you guys talking to That was pretty good. That was definitely.
They got together. Like it is very like ghost-like. He's got like Okay, so when you're done, you go there. So I'll hang out over here.
So maybe someone can be over here too.
I am.
Someone can be on my left.
I think I asked you. So what do you think of the
I'll stay here. This is like full solutions to our.
So what we have. I mean, I think it's like,
It's on that laptop.
like, for instance, the stuff that they were.
Hey, I saw you holding cord or something before. Is that just? How we do it?
I'd be hard pressed to see
Are people respecting space and technology? Do we need to tell her to shut up? Right behind you. Charged? Yeah. Oh yeah, you're in. I am on the stream. Yes. One of the streamers.
Okay. Did everybody make their way back to their seats to enjoy the rest of our presentations? Judging panel, are you all situated looking good over there? Ready to hear Space App Seattle has to give? Yes. Okay. So Team SD Density is up and ready to roll. No Logic is next. It's all yours.
Hello everyone, we are SD Genzi and we're doing a challenge Smash Our SDG.
Thank you.
And our team name is from the challenge and also her cat over here, as you can see, is really cute. And we're going to discuss if your city is developing sustainability.
Now, the obvious question here is, what's an SDG? Glad you asked. There are 17 SDGs just developed by the UN. They are goals you have to meet in order to consider it self-sustainable. I didn't know this when I started this project. Most people don't know this. And they're really cool. So we were trying to make a project that could help explain this to other people, broaden their appeal, because they're really good at gauging how well your city or country is doing at becoming self-sufficient.
So as Hunter stated, one of our goals was to raise awareness of these goals. So our web application, SD allows you to see how your city is doing at these 17 goals. And it also gives you the opportunity to look at volunteer opportunities in your area pertaining to those goals, such that you can kind of improve how your city is doing.
And with that in mind, we decided that by revisualizing and providing NASA's and the UN Sustainability Pact data to the public, SD Ganzi informs people exactly what factors are going to impact their region.
All right, so now that we've seen some background on our app, kind of the reasons we're doing it and how we're going to solve the solution we're challenged with here, let's go ahead and do a quick demo. You guys can even follow along at sdganzi.com if you'd like. So we'll go to sdganzi. And so let's first start with Seattle. Seattle, for obvious reasons, we're pretty interested in. And we're interested in how it's developing sustainably, how it's doing well against other cities, and where it can improve. So let's do Seattle. So D, that's actually a kind of an average score, even though it looks pretty bad. Most cities have a lot of ways to improve. So Seattle is doing pretty well in some areas, such as decent work and economic growth, but it has a lot of room to improve in some of these areas as well. So we want to give this tool to people so that they can see how their city is doing and communicate with others in their community to collaborate and improve. And one of the things we want to integrate there is we have the infrastructure set up to work with Volunteer Match, which is an API to match you with volunteer opportunities in your community related to these SDGs. But so far they haven't approved our request to use our API. So currently we are showing some volunteer opportunities related to those goals just with Google here until we have that API available. So let's go ahead and compare Seattle with another city here. We'll use San Francisco. And as we see, San Francisco is just a little bit better than Seattle. San Francisco is actually the best rated city in the nation with these goals here. But even San Francisco definitely has some areas to improve, especially it's got a 35 in affordable and clean energy here. So now that we've compared these, seen how we can do a lot of community involvement with these, let's talk more about some future goals we have for the product.
So just as all of our cities clearly have a lot of room for improvement, our site definitely has a lot of room to grow as well. So some of the things that we'd love to do in the future is integrate even more data to get more accurate scores. And then also offer more opportunities beyond volunteering. So possibly things like places to donate or good places to work, stuff like that. So there's a lot that we can do to improve our tool to make people more able to get involved in their community. Thank you.
Hey, that was really cool. I pulled up the app on my phone. I'm not finding San Jose, but I'll just go with San Francisco.
So a lot of the regions there are grouped together very closely. We have a total of 100 cities granularity here. So Seattle, Bellevue, Tacoma, those are all going to be in the same area of data.
Got it. Thank you. So I love the idea of volunteering, but one thing I was looking at was how does your solution monitor? Because it looks like you're taking current data as a snapshot in time? Are you doing anything to look at monitoring over time? Bless you.
So with that in mind, one idea that we wanted to incorporate but had limited time on was using NASA data that was compiled over, I think, 13 years. That way that you could monitor how improvement or degradation has happened to someone's environment or region over time. And one example of that we had was aerosol in the atmosphere. And that's small particles in the atmosphere that if you inhale them, it can be dangerous to your health. So we had a 13-year timeline that we wanted to display here on the website, but because of time constraints, we couldn't incorporate that fully. But we want to have a lot of data that was interactive. That way, when you got your score, you could delve deeper into what exactly it was that was affecting the score of your city so that you can get more data on that specific thing.
And just to check, the goals that you have and the scores that you have, this is from the NASA data, or these are the scores that you use by aggregating that data?
So, go down real quick. So on the bottom, the NASA data we use is global data, and we pulled North America specifically. And from the UN, we got the North America SDG data.
Thank you, Mr. Yancey. No logic. Up next, Lunar Insight. Lunar Insight, you are on deck.
Hello, everyone. We're Team No Logic from the University of Washington, Tacoma. And when me and my team were deciding our challenge, we all had the desire to help people and develop something that could eventually save lives. So that's why we chose the Surface to Air Quality Challenge. So we ended up creating an interactive data visualization tool. And so that anybody will have access to it and be able to search their city and see the air quality data and the associated risks with that. So we ended up using, for our data for today, data from Los Angeles, just for an example. So we chose Los Angeles because LA has the worst air quality in our nation for the past 20 years. In 2017 alone, there's been an estimated 7,100 deaths from the air pollutants. So that's kind of what inspired us to create this, so that people can be more aware of the air quality and all the risks that are associated with that.
Yeah, and we have to ask ourselves, like, how are we allowing these deaths to by air pollution to occur in our country? And the one solution to that is to get people aware of this situation. And so we decided to design a program that comes down to the general terms for people and allows them easy access to that air pollution data so that they can view it and then take action if they want to. So we decided to create a web visualization data app, and that will allow them not only to see the data every element by element, but also to interact with it.
So we've integrated some data into our graphs to allow everyone to be able to see the data from carbon monoxide, sulfur dioxide, nitrogen dioxide, ozone, and also a few more. Now we're gonna have our backend data analysis come up and show you guys a little bit about how our app works.
So here's a live demo. So here's a live demo of the app. It's a web app, and you can click. There's a street map of
area you're looking at in LA, and this is the pollution for the carbon monoxide here. There are buttons here, they don't currently work. And there's also a bar chart that we have for like the range from the first year of the data back to the last year. So the data set that we're using has about 3 million entries. So to ease our, it takes like 10 seconds to load in R. So we just did a period of 1 day span, and I guess that's it. Also, we have last thing. We have an example of what's. So this is an example of what the buttons would look like. So you would just, if you click the button for nitrogen dioxide, it would just show you the data for that pollutant.
How did you guys pick your name?
I guess we saw that there was a lot of data science at this competition, and we do not know data science, so we figured we'd try to do the best we could here.
What would your users actually use the information that you're utilizing for?
So they would do it. So one of the things we have the dots that we drew would be like pollution maps. So if you're in that zone, you could tell if you're going to be affected, and we could have maybe some stats on like how it affects your livelihood or stuff like that.
Could be something as simple as, hey, wear a mask today because it's high particulate pollution or something like that.
Just to check on those data visualizations. So you're saying there was a bug that was preventing them from displaying properly? And if so, can you tell us how it would work in the future?
So it wasn't a bug, we just, we were learning R in all these toolkits, so we don't have the UI implemented exactly correctly. We don't have the mapping to the buttons to changing the elements on demand, so we just did I'm not sure to show it on screen, but we just have the map, the pollution map change for each pollutant, and we also have the bar charts. Or there would be any type of chart, you could select different types of charts that would model how the pollutants have changed over time, like it would increase or decrease.
Thank you, No Logic. Lunar Insight. It's your turn now. Angry Space Birds, calm down. You're going to be up next.
There's 2 channels here for 2 minutes. If you can get me
Lunar Insight? Do you have Lunar Insight? Going once, going twice. I see Angry Birds. Okay, no Lunar Insight. You will have to find them another track. Angry Space Birds, come on down. SEAL Team 404, you are next.
So, hi everybody. I'm very excited to present the great people I had a chance to meet during this hackathon and the project we came up with after this today. As we can see, we are a pretty diverse group, but we had the chance to meet here, and what we have in common is the curiosity that we all have about space and our willingness to learn more, even if none of us have actually a background in astronomy. So we we want to spread our passion and curiosity, and we thought that the best way was creating an educational game. So we decided to pick the NASA challenge on build your own planetary system. Our main goal is to make new generation feel passionate about space and not feel intimidating. Me too, as was my first hackathon, I was kind of scared at the beginning because I felt I would be unhelpful. But thanks to this today, I overcame my fear and made this learning experience so much fun. And this is what we want to achieve with our game. So at the beginning, we looked at other space-oriented games, and we saw some room for improvements. And we want our game to be accurate on space and simple and also customizable. Our audience are young learners, that 65% are visual learners, so we think that this experimental tool will be very useful for kids to get hands on their idea and learn more about space by experimenting without feeling judged.
Okay, so what elevates our game from past games is how realistic the calculations are and also how customizable it is. You can change the size, mass, distance between planets, gravitational acceleration, and initial velocity. We can do this by using Newton's law of gravity, which is just relating the gravitational constant, mass, and like distance between objects. So you can do a lot with that. So what we did this weekend was solving just a simple n-body problem. In the future, we want to be able to just like add any body to the system. This is like the first look at our game. So this is what you get when you go in. It's very small, but there are like additional resources, instructions on how to use the game. The flyby camera lets you really explore the universe that you've created with any planet. And also, we have links to NASA blogs for people to learn more about the systems they're creating.
So with the hard work of Angry Space Birds and the awesome imagery and data from NASA, we were able to create some pretty awesome visualizations you guys want to see. So this is our ad right here, a couple screenshots. Just gonna go right on. The exoplanet, red dwarf, and home. So even though Angry Space Birds were very proud of the work we've accomplished, our original vision had a couple other things we wanted to add in, which was composition and just pretty much being able to change and add any attributes you like. So we believe this project impact is really mainly for anybody that wants to learn about space and really just interested. It's not intimidating and it's free and really the possibility of practice. So thank you.
Can you explain a little bit about the gamification? It looked like an educational tool, but can you explain how it's gamified to make it fun?
Yeah, so it's like basically you're able to kind of create like your own solar system. So you can like customize the planets by like different mass, or if you want to add like different compositions, like maybe there'll be like ice on the planet or like different atmospheres or something.
I'd like to add that this is more like Minecraft, where the point is build something, experiment, have fun doing it. It is not scored in any way, but it's a sandbox where you have no repercussions. You just go play.
Any more questions?
Can you explain a little bit about the data that was used and how accurate it is?
Yeah, so right now we're just using like the Sun, Earth, Moon system, but in the future we want to get information from the exoplanet API, and so like just get information about like all those planets and like use those actual masses and like the radiuses and just plug it into like the gravity, the law of universal gravitation. So yeah.
Thank you, Team Angry Birds. And I want to point out that Space Apps is about connections. Margarita, Team Angry Birds has a connection to someone in Rome who is also hacking, first-time Space Apps hacker in Rome. You're truly a global community. Okay. So, SEAL Team 404 is going, and then we'll have compute inputters.
Hello, everyone. My name is Avi Banerjee, and we're at SEAL Team 404. We're here to present Carpe Diem. We gravitated toward the challenge chasing the lost data, where we had to develop a computational method to recover lost data, lost or missing data due to signal sensor issue. Some questions arose around this challenge. In a mission-driven organization like NASA, how do they make their critical decisions with this missing data? And even with that missing data, how do they derive some insight from that? And it's not only a NASA problem, this is in many industries. When I was in the oil industry, I had to deal with lost data. As a data scientist now, I have to deal with lost data. So our proposed solution is using an ensemble of various cross-sectional time series imputation techniques, including mean, mice, KNN, and moving window to mitigate this loss. Our solution is completely scalable. It is an AutoML solution built on a GCP platform. It's easily adaptable for different data and file formats, and it's easily interpretable with our scoring metrics. So the user workflow is as simple as it sounds. The user goes to our web application, uploads some data, our different models are run on it, and the top ranked models are displayed in a dashboard format with the scores. So the first set of data set that we worked with was the NASA data set for the turbofan degradation, where it has 21 sensors. If you take that, go to our web application and upload it, it gets processed and you get forwarded to a dashboard where it brings in the data. The results are up top for mice, mean, fast KNN, and moving window. You can see the input data where there's some degradation up front. You can see the score and the computational time it took for each of the models. We could choose a specific sensor, and you can actually see where the loss is in the input data and how fast KNN and mice compensated for that with our models. Beyond this, after the successful implementation of this on this data set, I really wanted to see if we could do it on a data set that was personally. As you can see in this chart right here, my mom's glucose monitor experiences some data loss. We saw it in 2 consecutive days. So I figured, okay, we have this AutoML package, we'll just upload that data and see what happens, okay? When we did that, we found out that fast KNN yielded the lowest RMSE score, and a lot of those gaps were filled in. So on my next visit, I'm gonna go with my mom to her doctor. We're gonna try to give us this data and see if they can garner some more critical insight. So our technology stack was pretty Python heavy. We also included MPyU for a lot of those imputation algorithms. Those were used within for a Docker container and Flask and Power BI in a GCP platform. For future work, we want to add some more model offerings, including a Bayesian no U-turn model, spline polynomial interpolation, GANs, general adversarial networks for image data, NMF, univariate and multivariate options, validate our pipelines with other data sets, expand our error handling mechanism, and develop a more user-friendly dashboard as well. We are a team of developers and data scientists from a diverse background, and we are Carpe Datum, helping you seize your lost data. Thank you. Any questions?
So that was really cool. Thank you. I love the personal aspect. Other than visually looking at the data traces in your dashboard, what metrics would you use to evaluate, or what did you try to look at how well it's actually filling in the lost data? Did you do any kind of learning algorithms with sample data versus?
That's a great question. So a lot of the scoring metrics we did, right? It's hard to find. So the turbofan degradation data, right? So a lot of this data we didn't inherently just put in the degraded data. We took the original one and we actually created an algorithm that would randomly size the intervals of losses within the different 21 sensor channels. And then based on that, we had a muted sample of lost data, and we had a baseline of the actual data. And then once we pipe that in, we compared each of the models back to the source of truth, so to speak, and that's how we work with scoring that. But it depends on the type of interval, data loss overlap between the sensors too. So we really want to expand that a little bit on a diverse data set to see how it does with this RMSE, but then on some other scoring metrics as well. I'm sorry. There's this really, last year we did this visual interpretation of satellite imagery for refugee camps. And one of the bottlenecks for that, where we calculated the population based on satellite imagery, one of the bottlenecks for that was not only satellite coverage, but the resolution of satellite imagery. And a technique here we used again when we zoomed in on low resolution satellite imagery. Between the pixels, we could train the scan to be able to fill in the gaps there. So that's why this is such a powerful tool. So being able to put that in here, then we can just call this AutoML function to fill in that data too. And that's what we want to do. Our project from last year and this, combine it to really powerful product.
Okay. Impute inputters. You're up now. Do we have the nibbles? I don't mean like feeling like you want to nibble something. The team called the nibbles, which actually sounds more like a band. Okay, I don't see anybody thinking that they're called the nibbles and moving to be on deck, so we will skip them. Orbinators, you are on deck. Impute inputters, take it away.
Hi, we're the impute inputters. So the idea of imputation is taking a gap in your data and filling it into inference. And that's exactly what we're doing. We're focusing on the problem of computer vision. Humans are innately cognitive people, whether we're talking, listening to music, seeing images, we know what it feels like to see something and have it mean something to us. So the problem that we're facing is chases of lost data. As you take photographic images by sweeping satellites over the surface of a planet or of the body and glue the images together to make a larger image, you can have gaps in your data. Also, if you have data that's streaming down, temporarily you can lose your link and lose bits of data. So if you're sending an image of Mona Lisa from space to Earth, that data can be lost. So being able to fill it in is really important to us. You might not want to use an imputed piece of data to know that this is a good place to land your space probe, because it might be not accurate. But at the same time, being able to fill it in to get a reasonable interpretation of the world or the images that you have here is very valuable. So to solve this problem, we use a technique that was originally published called Pix-to-Pix. It's a conditional generative adversarial network, GAN. So the idea is that you, just like in speech, you can translate from English to French. You can take images in one domain and translate it to another domain. So this represents segmentation of images, and it makes a reasonable traditional photograph that's then generated as output from the model. Similarly, edges of an image can be made into a reasonable image that looks consistent with what we expect to be at first, right? So for our purposes, let me just say one more piece. For this purpose, when we have an adversarial network, we have two separate models that are battling it out and fighting each other. The generator, which consumes the image in one domain and translates it to another, and the discriminator that says, this image is fake, this image is real. So as the discriminator gets better, it says, you're not doing a good job, generator, you have to do better next time. So they fight each other and tell each other what they're doing wrong so they can improve. So let's look at our results. For this purpose, we collected a bunch of images from, I think it was JPL, Jet Laboratories website. These are images of the surface of Mars. So we had the original image that we downloaded that we chopped into blocks, and we degraded it by just chopping out 16 different small regions. And then we trained the network to try to fill in those gaps. Because we know what the answer is, we can see how well we're doing. And by eye, like we can see that it's doing a decent job. If you look closely at this, you can see some imperfections. In the very worst case, in this case, we had a very smooth image with little texture. It's very obvious that it's not doing a good job. And if we take a really successful case, it's very, very hard to tell that it's not doing a good job reconstructing the image. So much, in fact, that we're playing a trick here. This is actually reconstructed. This is the original. So what's next? This is all kind of hacked together in a weekend. There's lots of error analysis to be done. We had to downscale the model and make it fit on our GPUs because we're not rich folk. And the data was put together very quickly. We could expand it and do a lot better job of handling different domains.
So once we saw that it's pretty applicable, we wanted to try and put it on another challenge as well. So this was show the world the data. So we're going to take you through a demo since we're running out of time. But it's basically using a cycle GAN. This creates a mapping between two sets of images without having the images paired. So we used our set of data for training the model was Earth data that we scraped from Bing Maps, as well as images of Jupiter's surface that we found from NASA. And we, as you can see here, we are able to turn Earth into Jupiter, and then we can take Jupiter and turn it back into Earth. So our demo that we got running with one set of training data last night this is Seattle, and we are using live inference to call out to our service, and we're giving it the tile data or the tile image, and then it returns back an image that's been stylized to look like Jupiter. So now the user can interact with their own city as if it would look like a different planet. There's a lot of different educational applications once this model looks a little bit better if we have more training data, as you said. Thank you.
Can you talk a little bit about your stack and where you're fitting pix to pix in here and where you've done development on top of that, please?
So our development stack is kind of a standard data scientist stack, lots of Python. We have a Flask server that's supporting this web page where we're basically loading the Bing web app, and we're actively grabbing pieces out of the DOM and processing them into stylized Jupyter images and putting them back in. Your question about pix to pix, in that case, we have a data set that we built of about 1,000 images, where it's a one-to-one mapping of damaged image and complete image. In the case of Jupiter, we have spinning your eyes, about 1,000 Earth blocks and about 1,000 Jupiter blocks, and it's not one-to-one. Obviously, there's no image of Earth that's perfectly matched to the style of Jupiter and vice versa. The value of the cycle GAN is that it doesn't need a one-to-one matching to learn the style transfer. Does that answer your question? Great, okay.
So what are some good applications that you would use this for next?
I mean, there's lots of examples you can imagine where even imagine on Skype calls or something like this, you lose temporarily data flow. If the application can fill in those gaps in a sufficiently accurate manner that you don't lose information that's trying to be communicated across, that's great. Humans, we kind of do a good job of filling in the gaps for things that we're evolved for, but we're not evolved for having signals drop. So being able to just fill in the right frequencies is really helpful, for example. It's really tough to know all of the domain challenges of astronomy, at least I don't. I don't know if everybody else wants to jump in. But we gave some examples where images were not captured for all of the paths of a particular satellite that captures images at that resolution distance, or when data uplinks are occurring, like in the case of Mona Lisa, being able to fill in the gaps to some approximation. On the other hand, I know that we can also say to ourselves that there's techniques that already exist that don't use this kind of sophistication to fill in gaps. So I think I'd have to know more about the specific domains and how they've been dealt with in the past to say, where does this supply a lot of value versus more traditional applications that existed 10 or more years ago.
Thank you. Orbinators, you're up now. Debris hunters come next. And that will be followed by Uncrustable, which is the last presentation. Final instructions.
Try Windows P.
Hi, Doug.
Yeah.
So,
Escape.
what's that?
Escape.
Hello, we're Team Orbinators, and we took on the space junk video game problem, and like the world needs another video game. But it's the end game in this one that's going to make it matter. So the Kessler syndrome. So this is when a chain reaction occurs, one debris hits another piece of debris or another satellite, and it cascades and makes near space too crowded to traverse. So the Orbital Debris NASA office in 2005 indicated that if we never launch another rocket, it has already begun, as the 10 centimeter and below is propagating. So I think Orbinator will be a way to solve that. So in the beginning here, we looked at the data for the, he took the Celestrac data and put this in for different debris fields from past events. And that gave us an idea of what it looked like, so that would inform our model. So what we came up with was a series of scenarios, and the goal here was to educate the general user and the gaming public on the counterintuitive nature of a mission to deal with the space junk, so launch direction, debris, clouds, etc. And the idea here was if you get enough brains working on that they would come up with new strategies. And humans contribute to this well, because the situation changes over a couple of days with variations in space weather. So Matt here built a simulation in Unity of one of the equatorial cloud. And if you'll notice the mouse moving around, those are launch complexes, depending on the inclination of the orbit that's desired. And this here is the our carrier vessel, which has little drones on it going into.
You'll notice that as you choose different potential orbitals, it has an impact on the amount of fuel you have to go and send out a drone to collect the debris. As you move up or down in orbit, it uses up more fuel than moving in or out in altitude.
So when we get up into position in HUD, and this isn't a 2D spatial display, this is an orbital energy display. The white lines are basically the drone energy profiles in 2 dimensions, delta V and change in inclination. And everything on the screen is also a control. So we're down, what is the end game? Kerbal Space Program, plugged in, get 100,000, 1 million users attacking the live information for the cloud. And in 5 years, we go take some of those Kerbal designs and go, hey, here's $1 million, go hunting, people. Because right at this moment, nobody's dealing with the problem. Thank you.
Questions?
Could you elaborate a little bit on gameplay and how that would work with your model?
So basically, so the way the game works is that you start from Earth and you have to decide based on the debris clouds where you're going to try to go to collect the most debris. The objective is to clear out as much debris as possible. So once you select your appropriate launch site, that's where the general location where you have deployed your mothership, where you send out additional drones from. Now you have to, based on your analysis of where the garbage is relative to yourself in orbit, you have to decide where you're going to place the drone in order to collect the most trash, and based on your fuel usage. So we have to balance the trash's location relative to you to pickup potential. And then you score points, or in other words, research dollars, by proving the efficacy of collecting trash, which gives you better technology so you can continue to do better at this and continue to grow through the game.
And we also have a web app that can visualize all the different debris from different explosions in the world. And you can actually go to the link and click it and see that in your phone. It's deployed already.
And we would use this data visualization, the data collected from NASA, to inform our model and try to show where the trash is, so you can make those realistic decisions on how you plan your mission.
Thank you. Okay. Down to the last couple, we've got the debris hunters now, and Uncrustable will be the last presentation before the judges go into deliberations.
anyone use a Mac earlier? Oh wait, do we have something? Okay, awesome.
Look at this explosion.
We lost it. Did I step on something?
So let's take a look at this explosion. This is what would happen when we don't collect the junk that is currently on our space. This will destroy all future investments on our space currently. There are more than 20,000 space debris floating around our space right at this moment, and millions more that have yet to be found. Now, we all know this problem will ultimately factor into our ability to explore space further and further give us the opportunity to further explore the opportunities that space will provide. Now, my team is a student-led organization and we are called Debris Hunters. We developed an approach to combating this space junk and using a video game to help engage the public good and raise awareness for this space junk.
All right. Hi. Let's make this a little more personal for a minute. So can I get a show of hands? Everybody who used a GPS-enabled app this morning to get here today, Citymapper, Google Maps, Lime, Uber, Lyft, etc. So it's a lot of people. So you depend on satellites, GPS satellites, to get around town. We depend on satellites for other things like wildfire tracking, earthquake prediction. And the problem is there's a hidden threat to our way of life that we don't think about very much. It's called orbital debris. It's flecks of paint, pieces of metal, pieces of electronics that have sloughed off of satellites and spacecraft over the last 50 years or so. And it's threatening to damage services that we use every day. It's spinning around the Earth, threatening mission-critical infrastructure, business-critical infrastructure, and we need it to do our jobs. We need to get around. The goal of Debris Hunters is to raise public awareness of this problem and give them a way to take action. So space debris, orbital debris, is a known and growing problem. Countries like China, companies like Astroscale are starting to work on this. And you can't just shoot your way out of the problem, at least not the way you might think.
So speaking of shooting, let's get to the fun stuff, the game. So I just wanted to point out that it's mostly C# and Unity, and then Avi is going to give us a great demo of how this game works.
So as you can see, there's a lot of satellites in the sky, and these are meant to represent orbital debris. And whoops, I just fell off. It'll reset. Anyway, so this is a space station. This is meant to represent the kinds of equipment that would be at risk. So as you can see, I can shoot down this debris with my laser gun. The reason why it's a laser gun is because most of the ways that people use to combat debris is with laser guns or lasers and all kinds of things. That's why I use a laser gun. And at the top of the screen, you'll see the UI is kind of messed up, but whatever. That's supposed to represent the Kessler syndrome. So if you can see, as I get hit, slowly it will go towards the red, which means that I'm getting closer to the Kessler syndrome. And so you will watch as I slowly die. And also on the bottom left, that's my score. And yeah, that looks fun. There are sound effects and everything like that, but I guess it doesn't work. Yeah.
So if I quickly wrap this up, if we go back to talking about the game, what you didn't see there was the Earth. We've actually used the NORAD data to model what all of the pieces floating around the planet, and so that's using the stuff that we've downloaded. And then if we go back to our presentation, so the final stage of this game is actually a call to action. So we want to give people this screen saying we need an international space debris policy. We want to have a clickable button saying you can contact your representatives, here's some language, please ask for policy. Because we want to educate, we need international enforceable treaties, and we want to get to a point where we can require satellite launchers to actually participate in debris management. That's the far goal. This goal right here with this game is to educate and entertain and grow awareness of this problem. So we don't want this future. Questions? And I'm very sad the sound effects didn't come through.
Oh, that's too bad. So I'm a big fan of lasers. Can you explain how lasers work to remove space debris?
I believe that the lasers they use on mainly smaller things to slowly like push it towards Earth's orbit to deorbit them. And I don't think they use lasers for bigger objects. They would mainly use maybe like a harpoon or a net and small little cube satellites to like attach onto them and use their thrusters to bring it down. But lasers, I believe it just like slowly pushes them back into Earth's orbit. Yeah, and
Which orbits were you focused on for the game? Like low Earth orbit, medium Earth orbit, geostationary?
I believe it's low Earth orbit, and that's where we modeled the data.
Incredible, you've made it to the end. Uncrustables, come on up. After Uncrustables, we'll have a break. There will be some cake. The judges will deliberate. You may be called to provide additional information. They may come around to ask you questions. So don't go too far.
Are you going to use the slides? I'll tell you next slide.
oh, it is me. Oh wait, I'm on the wrong one.
First, even spoilers.
I know, I'm checking on.
Okay. Hello, everybody. Our name is the Uncrustables. We're UWT students. What we've made is an approachable design for, again, the space orbit problem. Can you go to the next slide, please? So obviously, we're working with the same satellite debris that everyone else is working with, but ours is targeted to even younger people. We want something that's more approachable for an adolescent mind, because an adolescent mind is more plastic. So it can develop along with the problem instead of having a developed mind try and think of how to cure the problem. They compare things like they compare things like imagination and creativity that a developed mind doesn't really have anymore, which can lead to a future where we have more creative results. A goal that we didn't put on here that I think would be good is like Space Apps 25, maybe there's so many people that we need 2 or 3 venues. Next slide now. Okay, yeah. So we want to raise the awareness of the orbital debris, but everyone's already talked about that, so I'm not going to talk about that. We want to educate the next generation through the use of an interactive experience. So our game isn't shooting lasers. It's not anything that requires physics or science. It's more of facts. We display the facts that NASA has provided, and then we set scenarios so they can kind of walk through them and figure out, like, oh, this is what's going on right now, so this is what we might need to do in the future to fix it. Go ahead and go to the next slide. And this is over here.
Okay, some ways we want to implement our app or web-based app is to actually make an impact. So not just educational, we want to fund using maybe partnerships affecting people on the global scale. So our global issues affect, well, if we let the problem go on like that, it will affect everyone on the global scale, but also people in space right now. And then Kessler syndrome was already discussed. Can you go to the next slide? So how we want to implement profits of our app is maybe monetize our app, use microtransactions. I don't know if you guys have heard about Ecosia that use their profits for environmental stuff. We could do something like that with our in-game currency, and then incorporate game scenarios. So more data, more levels, because this is just a design. And then Abe is going to run you through a scenario.
Yeah, so we do have a game link through the GitHub page. So if you guys do, you can use your phone and your laptops to click on this link. And so we're going to do a live demo. So here we see the ozone layer, and this will be our HP, kind of determine how much orbital debris has crashed onto the Earth and done away to the ozone layer. So we have a scenario, and we have 2 options, one being the right one, and the second one being generally bad. So let's go with the bad option, yellow the titanium satellite. So you can see our HP goes down, our ozone layer is not doing too good. So you have encountered fiberglass, so let's do something good, release next. So now we have a shot, so let's now do a boost. Let's try growing some trees, and now we have a boost. So let's leave the shot, and let's go back right into the game. So now, give it a sec, and now we have another one, and let's do something bad. And now we have Tesla, so we should also take that into account. And so they tell us, congratulations, but there is a site, and they're saying, well, you didn't reach 100%, so why not look into the site, which is basically a NASA government link that tells you about what we agree. So let's see, what if we do it correct? Like, what if we do 100%, right? So fire lasers, release the nets, leave the shop. And then send a robot. So they'll say congratulations, but they'll give us a special reward. With all the scraps that we gave them, they recycle and give us a rocket.
Thank you. You guys talked a little bit about microtransactions. I was wondering how you might incorporate it into your gamification.
All right, so the first thing we thought was if your ozone layer was getting too low or your health was getting too low, you can maybe get a health boost. You just buy it straight up microtransaction. That's the most basic method. Of course, we don't want to go too far into like loot boxes or anything. I don't know if any of you know, a lot of companies are in trouble for that, like child gambling. We don't want to mess with that. And then we can also have these shelves are empty up here, where we can put different items that they may be able to purchase. And another thing we were thinking about implementing was a character creation. So like a person, they wouldn't just come out here and play the game as a fake. They would make a character so you can see what they look like in the space realm. And you can have microtransactions where they can buy more costumes or buy more character skins and things like that. Any more questions? Groovy. Okay, cool. Thank you.
Okay, so made it through the presentations. Judges are gonna get deliberating, but before we do that, did we say cake? Did we mention that we have cake? Look at this amazing Space App Seattle cake that we'd like Space App's co-founder Taja Zane to come up and give a cut before running off to the deliberations chamber.
We'd also like all of the organizers to come up because it took a team of people to put this whole event together, and we want to recognize that it took all of us. We would not be here without you, Todd. No.
Oh my God, how do I do this? It's easier starting a global hackathon than it is when
So Todd.
Oh, that's the focus ring. That's the focus ring, Rudy. Awesome.
So Todd, before you go, we would like to give you from all of the participants in our hackathon a side thing.
Amazing. Thank you so much.
And Ray, we have something for you from the organizers.
It's a Christmas cracker.
It's a big Tootsie For all of the tireless hours that we worked on this together. So in those long nights in the winter, you can snuggle with your family and learn the constellations as they glow in the dark.
Glows in the dark, awesome, thank you so much. Okay, hackers, you can start heading to the kitchen when the cake makes its way over there and grab some slices. Judges, let's go to your chambers.
Yeah. Are you sure you want?